Most of the volcanism and the magmatism on our planet actually happens in the oceans. Submarine volcanism is one of the fundamental processes that has affected both the composition of our oceans and the shape of the seabed and the development of life on the planet. And the environment that we're in here in the Kingdom of Tonga is near a subduction zone, but just behind it. We're looking at a place where there's a large diversity of volcano types and volcano age and the types of eruptive products that they produce. And what we're really trying to understand is, how does an individual volcano grow over time? How does it influence the next volcano nearby? How is magma partitioned between those various volcanoes? How does the style of eruptive activity of those volcanoes control what happens at the volcano, the development of hydrothermal systems, their colonization by organisms? The whole pantheon of processes that cause and allow volcanism to take place in the oceans are well reflected here in a relatively small space. So in addition to studying individual volcanoes, we can compare and contrast across closely spaced volcanoes.
There were a number of ways we chose where to dive with the ROV. The first was we wanted to concentrate on the whole group of monovolcanoes. So there's 9 volcanoes that all have this unusual bonanite lava composition, to see what stage they are in their volcanic evolution so we can compare them to one another, try to figure out why some of them have the hydrothermal systems and other ones don't. Also, there's some huge lava flows of a different composition called dacite to the west of the Matas. And then the final thing is we wanted to make dives at some of the most recent eruption sites. What's been exciting is we've discovered several recent eruption sites just on this expedition. We were able to make dives at all those sites.
Excellent work there, J-Rod. It's a good piece. I like it. It is super fat with crystals, and you can see actually very beautifully the olivine and the clinoptertine. And in she goes. That rock is destined to become an important part of our understanding of volcanism at West Mata Volcano. When we go under the sea, it's hard to get that overview perspective of the volcano. We can't see very far with our eyes, even aided by very strong lights. And so we tend to be focusing on smaller structures on the volcano. So what we're really interested in is looking for pieces of material that are representative of the phenomena that we're trying to observe. So the fieldwork is really just the first part when we collect samples of volcanic materials. But the real work begins back in the lab. We take the rocks apart, both chemically and physically, all designed to tell us what is in the rock, how did it form, how did it come to be what it is. And this can take months to years.
The kind of rocks in the volcanoes have an influence on the water chemistry and therefore probably on the life that's living on them. Magma generates heat, water reacts with the hot rock, changes chemistry completely, and comes out and provides a big source of energy to animals that are living on the seafloor. So basically, chemistry is the medium between rocks and life. So when we look at these Mata volcanoes, the one that really stands out as different from all the rest is West Mata, which we know has erupted. We've seen it erupt. And when it erupts, the chemistry there is completely different from what you get in the typical high temperature black smoker type systems. And all of the rest of the Matas, the North Matas, they have that latter, more common high temperature system where water is penetrating deep down and mining out chemical energy from the heat source and coming back up to the seafloor, forming big chimneys. The chimneys are a habitat for the animals, and we're really still trying to piece together what are the rules that determine what animals live in each of these different sites.
It's hard to pick the most exciting things that we've learned on this expedition because we've learned so much. The top one for me is the diversity of volcanic styles. In addition to the wide variety of eruption styles, there's also a lot of what we call mass wasting, syn eruptive tectonism, breaking of very steep slopes and making rock fragments. They all combine together to give us a really unusual volcano shape. The next kind of really fundamentally interesting thing we've learned is that even in very, very closely spaced volcanoes, the differences between volcanoes are stark. I think now if you dropped me down in one of these 4 volcanoes that we know have a hydrothermal system and didn't tell me which one we were at, I could tell you just by looking at it, because the style of the hydrothermalism, the shapes and spacing of the chimneys, how tall they are, what's living on them is really very different from site to site. The third really interesting thing that I think we've learned is that volcanism isn't just restricted to the summits of the volcanoes. A lot of these volcanoes have been active on their flanks and at their bases, and the diversity of locations on the volcano where volcanism can happen is really something that excites me, and we'll be investigating in much more detail as we try to explain the differences that we saw.